Okay, so we have coming to the fourth lecture for this tutorial. We're going to talk about visual decoding. And the idea is that if we have the, visual encoding selections, attentional selection, given this, what should be the decoding? Yes, the idea is if selection and attentional bottleneck starts at V1, what should decoding do in light of it? Yeah, and so after the morning lectures, it seems like as if my, I did not quite say attention clear enough. So let me also repeat in another way, because also the first lecture was a bit cut short. Okay, anyway, the content for this lecture is some highlights of the decoding of biological vision. And first of all, we're talking about decoding regardless of attention. And then in light of attention, what should decoding do? Yeah, so that's what about. So let me just review what attention is. Attention means that information through the camera coming to the eye and sent to the brain is 1 megabytes of information even after compression. Okay, 1 megabytes per second. It's really quick. However, attentional bottleneck can only get less than 1% of it. That's what attention. Attention means delete most other information, only select a small part. That's by definition attention. And so whatever you deleted, you cannot do visual performance about it, performance report and all these kind of things, or slow and so. And so are you sure you deleted most of it? Yes, let's have a demo. And then can you tell the difference between these two pictures? If you have never seen it, you say, gee, these two images look the same. If you haven't deleted anything, you should see difference right away, and that's the engine, yeah? And so therefore, this is a particular evidence showing that, yes, you delete most of it. And so we're nearly blind. And then you say, how do we delete? How do we pay attention to the things that we don't delete? It turns out that in visual behavior in humans, it's by eye movement. Whatever you move your eye to, you don't delete, okay? You say most of the time. This is in natural vision, in natural behavior. You pay attention to here, this is 1% information, that percent. You move your eyes 3 times a second. So therefore, to know how do we pay attention, you start from eye movements, because that's the natural behavior, okay? And then people studying say, oh, it looks like just before an impending saccade, object discrimination is best at the destination of saccade. So imagine your gaze is here, you're about to make a saccade over there. And then let's say you flash on a letter for people to recognize whether it's letter A or B or C or D. If you flashed here, people can do better than if you flash there, because there is where they are just about to make a saccade. Okay, that's an experimental fact. So therefore, our saccade and attention is intrinsically related. That means whatever you're about to saccade to, the information there is going to be selected and not deleted. Whatever you're not paying, that's attention, okay? And people have also shown that it is possible to keep your gaze fixed while directing. So first you say you have to keep your gaze here, don't saccade there, okay? But trying to see whether it's a pair of shoes, a pair of gloves, you could do that, even though that's unnatural. People have found that it's possible. So therefore, you can select that piece of information versus that piece, you can select here versus there. And so it's possible. That means you can do visual performance here versus there and so, yeah? And can you saccade to one location, but pay attention to some other? So for instance, you're about to make a saccade there, and a flash letter here versus flash letter there, basically it's not possible. You saccade to one way and pay attention to something. That's psychologically behavior experiment done. It's not possible, difficult, impossible. Can you pay attention to 2 different locations? Not possible. You have to pay attention to one location first, then go somewhere else, okay? And then by definition, how do you say, what do you mean by pay attention? As I said, by performance, you say, oh, performance 90% correct, 95% correct. This is a measurement to show that you paying attention, okay? So for instance, it can make your performance faster, it can make your performance accuracy higher. So for example, in this example I've shown you, that imagine you're supposed to fixate here, you're trying to pay attention without moving your eyes. Imagine, okay, you fixate here, and then after a while, time goes this way. After a while, there are going to be 4 things appear in these 4 boxes. One of them is going to be letter T. You're supposed to say whether it's like letter T is the right way up or upside down, but you don't know whether it's going to appear here or here or here or here, okay? So therefore, you're fixate here. So if it appears here, your attention already there, you're more likely to do it better than if it appears here, your attention goes somewhere else. So you can make your attention go there by just before it appears, some light flashes there, then your attention will automatically go there just by that flash, even if your gaze doesn't go there. Okay, but if it flashes there, this T is here, then you will get worse. So therefore you can see the difference. Or you can direct attention by somebody tell you, hey, it's upper right, you can tell you that way, and then go there, it will help. Yeah, and so you can see that you can do this task better in accuracy and in speed. And that's how you can measure, not just hand waving, say your attention there, you can actually measure with objective measures. Okay, and so there's flash and things like that, you know, can accuracy higher, accuracy lower, you know, that difference is a measure, objective measure of attention. That means you did not delete that information versus deleted that information. That's the idea. Okay, and you can also be faster versus slower, and that these are the way of measuring whether you pay attention. Okay. Okay, and then the whole idea, and then say which brain area is doing that. Then you say, okay, let's see which eye muscle movement coming from which brain signal. They realize it's a midbrain area called superior colliculus. Okay, anyway, superior colliculus is where go to the eye muscle, move your eyes, because that's how it goes. Then it shows, oh, which brain area is projecting to it. V1, LIP, which is in the parietal area, and frontal, they project to it. So therefore, you can imagine this is the executive secretary, they're having multiple bosses. They say, which boss is bossier? Yeah, more important, you can say like that. And you call this bottom up, and this is top down. The reason is V1 is basically, you know, before object recognition. And then you can say which one is more. Here's a demonstration of bottom up and top down. Imagine you have a task for you to look for a uniquely oriented bar, then you have a top down goal, you have a task to look for it. And therefore your top down attention should make you look at there, but somehow your bottom up attention make you automatically distracted to there. So therefore there's a bottom up guidance of attention. And this paths come from here, this paths come from there. Then people say, which one is more important? Well, turns out that transiently the bottom up will trump the top down, because it just have to distract you to save your life. Okay. And you can also say, what about sustained version? Well, you can try to, okay, forget about the bird chirping outside just this lecture. You can also suppress after the initial transient bird chirping. Yeah, that you can also do that. And so that's the idea. And you can also, you know, here's my way of, another way of looking at it, because your eye moves 3 times a second, and therefore you move 180 times per minute, and looks like you're only aware about, 10 times of them. So therefore, there's lots of eye movements are completely involuntary, automatic. So that's another way of saying bottom up is actually quite a lot. Yeah. And so therefore, you have a very important question is, you know, the obviously 99% of information is deleted. Where does the deletion happen? Does the deletion happen in the retina, the next stage, next stage, next stage? It looks like in V1, you still have it. So what we did last lecture is say a delete starts in V1. Now, why do we say delete starts in V1? Because last lecture we talked about that V1 guides your eye movement. V1 signal really make your eye move in a way that you don't even intend to, even if you're doing a task of reading this book and then suddenly something. And so therefore, this is going to make you completely rethink about how the brain should do decoding, because the idea is you select these 2 sentences in the book to read before you even read it. So once your eye moves, then you say, well, looks like maybe selection starts. Okay, starting from V1 downstream, you start to delete. Do you delete 100% right away, or do you delete only 50% of the way? Then you delete 30%. This is an empirical question you should we could find out. But nevertheless, whatever that's not deleted supposedly is then recognized. And so in this context, let's talk about how does how does decoding works. Yeah, but imagine if V1 doesn't delete it, V2 doesn't delete it until V3 starts to delete, then you're going to design your decoding differently. Yeah, and so therefore knowing that V1 is starting can give us a hint that what's going to happen. Okay, let's first of all just look at some phenomena, get some think, reflect, ponder about it. Okay, so for instance, here is the inattention blindness. I kind of already told you what's the difference between these 2 pictures. It's just very big, you can't tell. And here is something else. Remember, selection is move your eye. So therefore, vision is looking and seeing. Looking is to select which bit not to delete. Yeah, and here is a phenomenon showing you that looking and seeing are completely can be separated. Okay, so imagine here's a picture, and you will probably see something distinctive that should attract your gaze. And however, if you put most of these letters in one image to the left eye, except for this letter, you put this in the right eye. Okay, so all letters here except for one, put in this eye, what you will see is still the superposition of all these letters. You could not tell the difference this letter from any other letter, even though that's uniquely to the right eye. It turns out that your gaze will be automatically attracted to it, even though it does not look distinctive. Now, because the signal regarding which eye sees what is only in V1 and retina and not in V2 and later. So therefore, here's a hint that V1 is directing your gaze. Yeah, that's a very strong evidence. And therefore, and also because you cannot tell the difference between this X and other X, this is the evidence that you're looking without seeing. Yeah, and so therefore you can see the vision algorithm decoding is after looking is possible. Yeah, this is the evidence showing it. And here is another example where the decoding kind of strange. Yeah, you can have a random dot to one eye. You can put another piece of random dot on top of it. Doesn't show the difference because there's nothing different statistically. And you can copy it to the other eye. But if this this patch, which I just outlined for you, if I don't outline for you, you wouldn't know the difference. Yeah, and let's move it to a little bit that create binocular disparity. Take the border away. Somehow our brain can tell there's something is in front. Okay, so the brain somehow this is a particular decoding performance, right? And we also have this strange decoding performance that's called visual crowding, that if your eye gaze is fixated here, you can see both letters to the left and right. And that means your camera, your retina has enough acuity for you to see this. So the retina can still do that. Okay, no problem. However, if you crowd this T with other letters, they are not overlapping, but if you keep your gaze fixated here, somehow you cannot see this letter anymore. This T, yeah, you cannot recognize. So this is not because your retina cannot, optic quality is good enough, it's your brain, yeah? So there is strange decoding performance there. Okay, that's interesting. And here is another strange decoding performance where you can see A and B looks one dark, one bright, but actually on the image, they look exactly the same. So your brain somehow does this transformation to decode the brightness of this patch, strange, yeah? And here is a strange example where you can decode the existence of a triangle, even make this triangle wideness seem to be even wider than that. That's a strange decoding performance. Here is another strange decoding performance when you see things kind of rotating clockwise, but in fact, it's all illusion. You can look at this patch, it's not moving, rotating at all. It's just keeping back and forth, left and right, and it's not. So somehow your decoding can have errors, and this error is reproducible from one brain to another. Almost everybody can see this illusion, yeah? And from these errors, you may be able to debug and say, what is the algorithm in your brain, hopefully, yeah, we'll show that. And here is another error that's very interesting. You can see a lot of flashes, yeah? Do you see lots of spots flashing? Yeah, are they real? They are illusions. And wherever it is, just stare at this spot, it's not flashing, right? It's flashing in wherever you're not staring. So somehow the error in your central vision and error in your peripheral vision is different. And in this case, the error only happened beyond your center of gaze. Okay, that's very interesting. And here is a particular decoding situation that you don't know what this is. What is this? Oh, they look like it's just completely random patches of image patches. However, if you accrue them by something, suddenly you realize they are all letter B's, yeah? And so that's an interesting decoding performance in your brain. And here, what is it? You know, it's you may say, what is it? You can look for a while. Some people look at immediately see it. Other people don't see it. This is a Mooney image. So somehow your brain is overwhelmed by this and could not decode. But if I give you a hint, then suddenly it's all vivid. You can see it all absolutely clear. So what is this decoding? Is this a top-down feedback or what is it? Yeah, you can see so vividly detail. Yeah. And here is a ambiguous decoding outcome. You could see a vase. You could also see two faces. And these ambiguous perception is yet another way to probe the algorithms in the brain. And the people use binocular rivalry is another way of probing the brain algorithms. For instance, put this in the left image, the right image, what do you see? It turns out our perception just kind of oscillate between these two by a period about 1 to 2 seconds. Yeah, it's kind of random like that. Here is something also interesting. You know, you can do something. Imagine you ask people, you see this image very quickly, but immediately removed, and you get to answer question, how many bars are cardinal? Okay, the answer is 3. Yeah, and this is a where task. It turns out that you can just show the very briefly whether it's 2 or 3 or 4. The amount of time needed to answer this question correctly is independent of 2 or 3 or 4 cardinal bars. However, if you ask people this question, are the cardinal bars uniformly oriented? In this case, will be no, because 2 are horizontal, 1 vertical, right? Then how long do you need to show this before people can answer this question adequately? Grows with the number of cardinal bars in the image. So this is called a what task. It's a what are these bars? Where task, where are these odd bars? Yeah. So depending on what you decode, whether you decode identity, location, it requires different amount of visual input time. So that's also kind of a hint for you to do things. Imagine you ask a monkey to say, oh, is there an odd bar in this image? The answer will be yes here and no there. Turns out that for monkey, if you take off their V2, they can still do that. That's interesting, huh? But if you show them this image, you ask them, is the foreground region horizontal or vertical? The answer is vertical and horizontal here, yeah? And if a monkey, you take off their V2 or take off their V4, they can't do it. That's another way to hint to us what could be going on, yeah? Okay, and here is another situation to show you the looking and seeing and decoding may be interesting. So I asked you to look for a uniquely oriented bar in these 2 images, and it's very quick. You'll see it right away, yeah? And if you heard my last lecture, you realize this is the most salient location, and V1 will fire a lot for this location, attract your attention. That's why you see. Now imagine on each of these images, on each bar, you add, superpose on it a horizontal bar or a vertical bar, okay? And still trying to see where these 2 uniquely oriented bar is, okay? Where is it? Somehow this is a bit hard here, easy there, yeah? Why is that? Yeah, it's here, no? Okay. Turns out that in our recognition of, it turns out we have rotation and reflection invariance in object recognition that interferes with detecting a unique salient bar, because this is a letter X-like shape. It's a shape like a letter X. It looks exactly the same in shape with the neighboring items, except rotated and refracted, and that confused us. But this is a skinny X, so it doesn't confuse us. So therefore, our decoding is reflection and rotation invariant. That's interesting, yeah? We have viewpoint invariant in our decoding, you know, the lighting invariant and size and so on. And so therefore, let's define decoding. Decoding is when you have a 3D scene. Imagine, you know, some aspects of scene, for instance, a dog's velocity, the identity of face. And this scene is denoted by S, stands for scene. And then we visual system we hit a scene, and the visual system somehow sample or represented by some vector R, which is the response of a population of neurons, let's say, okay? It could be a retinal image, neural responses from the retina or cortex or so on. And found that you want to infer an estimation of S, we call it S hat. And that's by definition decoding. Of course, not only you have this R, you don't have access to that. All you have access is neural responses R, yeah? And you have other information such as internal expectation and so on, yeah? And then you have this estimation, and that's the decoding. And this decoding, for instance, people can have different ways, you know, can build a neural network for it and all kinds of stuff. Neural network go from R as input and feed forward with a decision S hat as output and so on. But another approach is like a Bayesian approach. Some people like to do it that way. So for example, let me just give you an example. Okay, imagine that you have a scene. The only property you care about is whether a group of dots mainly moving upwards or downward. There's randomly moving dots, but there's a trend of moving upwards, maybe in this example. So overall motion is upward or downward. So the scene has only 2 classification label, up or down, okay? And then imagine that your neuron, let's say neuron, just one neuron, found an MT neuron, and it's firing in such a way, the probability of firing given any scene, up or down, is that, let's say, the non-prefer, it may be like preferring down or up, you know, is this probability with this mean and this distribution. And another one is that prefer just means it will fire a bit more, so therefore, obviously, it's shifted this way. And from that, you will have to, given a particular value, let's say it's firing this, okay? Then you have to use this posterior, yeah, given the R, what should be S distribution. And then from that, you say, okay, maybe I pick the S that maximize this posterior distribution, and that will be my estimate. So that's the Bayesian approach, yeah? And Of course, you could be wrong because, you know, what if the eyes happen to be here in this area? You know, you may give a wrong estimation. That's when the decoding error happened. And maybe illusion is one of those, or, but maybe sometimes it could be just, you know, some, but anyway, you could happen to be wrong. And how wrong it is depending on how separated these two distributions from each other in that peak, as well as in the variance in terms of stochastic noise. And this is usually measured as D prime in psychology. As you imagine, this D prime larger, the less likely you're going to make an error, and that's as you can imagine. And then you can plot the probability that your estimation is actually correct versus the percentage of dots moving in the S direction. So for instance, here maybe, you know, 50% dots moving that way, the rest is not. And so of course, if 100% moving that way, you're going to more likely to be correct. And so therefore you can see that indeed this will be more and more correct. The probability of approach 1 when you have more dots moving coherently one way and less otherwise. Yeah. And interesting thing to note. Okay, first of all, these are data points. Data points dots are from a single neuron, such as this, you know, just having this probability of firing. That's it. This neuron just prefer one directional movement over another directional movement by its firing rate. Okay, one direction makes it fire more, another direction was going to fire less. Just by a single neuron, you could do that, just using this Bayesian algorithm. But you can also make the monkey press a button to tell you whether moving one way or another. And the monkey is by these open dots. It looks like a single neuron in the MT cortex can do as well as a whole monkey. Does that make sense? We don't know if that makes sense or not. That's the experimental data. Okay, the monkey usually are trained very well for doing it because they have to work for their cell, have to work in order to get drink, yeah. And so what's going on? Yeah, funny. But anyway, you can also extend this approach to a population of neurons, not just one neuron. So imagine you could have n neurons that are responding R1, R2, Rn, and you can do a feedforward into a weighted sum of the response and put this, you know, as say you're going to distinguish between two situations, which is A or B. So here is a response under B. This is the response distribution under A. You know, originally A and B is moving up and moving down, but could be anything, A, B, yeah. And it turns out that if the neuron having Poisson distribution and is conditionally independent in its stochastic noise, then you can have an optimal weights that design this way, which you can do that. And this you can actually implement the neural network with a feedforward weights. You can prove the statistically most optimal. And with this in psychology, in neuroscience, people start to say, can we then use the retinal and the V1's neural responses, because each, you know, we know exactly how is their, you know, how they're responding, especially retinal V1 neurons. You can measure them, you know their properties. Can we explain perception? So for instance, A, B could be, do you see a face? Do you not see a face? Is this Mr. Smith or not Mr. Smith? And so on and so forth, okay? So let's apply that, okay? And then one thing you'll notice, the more neurons you have, the more D prime, bigger the D prime is, so therefore you should perform better, yeah? Remember, we were a bit surprised that somehow the whole monkey and the one neuron performed exactly the same in terms of performance. Well, let's see some other examples, okay? So let's try that. And then, for instance, here's an example. They usually call that ideal observer analysis because you can say that this is optimal decision under Bayesian statistical decision making. Yeah. So imagine you have an example. The observer has to answer: is the image A or B? B is having no, it's uniform, and A is average the same grade level as B, but actually it's a grading non-uniform. Oh, A or B. Okay. And then you can say, what is the minimum contrast in A necessary in A in order to answer this question adequately? That means performance accuracy should be above, let's say, 80%. You can define a particular threshold, say adequately. And then you can then go ahead and measure, you know, contrast sensitivity, which is the inverse of the minimum contrast necessary, versus the grating spatial frequency, because it could be, you know, low frequency, high frequency. And this is what you get, okay? And the data points are the observers at 3 different overall mean level of light. And the curve is in fact from this optimal decoding coming from the photoreceptor responses that everybody knows because they are very well known biologically, physiologically, how they respond to light. Yeah. And so the good news is data match prediction. Fantastic. Yeah. Here's the bad news. Except that the prediction found the optimal decision have to be scaled down by a factor of 21.5. That means we are doing much, much, much worse than what our retinal neurons would enable us to do if we are ideal decision-making machines. Yeah, interesting, huh? Okay, let's have another example. Here's an example where you are trying to do contrast discrimination tasks. So rather than trying to distinguish A and B, there are two examples. In fact, A and B and both have gratings. One have a little bit higher contrast than the other. Then you say, what is contrast C? The other is contrast C plus delta C. And then you can say, what is the delta C needed? Contrast discrimination threshold needed for you to answer this task well, do this task properly, versus the baseline contrast. And again, you find it looks like that the human and monkey behavior is equivalent to if you only use 71 of V1 neurons in monkeys. V1 has 100 million neurons, and you just use 71 of them, and somehow they're equivalent. That's also surprising, isn't it? Yeah. And so all these are kind of here's a third example where there's a color discrimination in a monochromatic light. We know we have red, green, blue cones, and these are the sensitivity to different wavelengths. This is just sensitivity in the log scale. And you can have monochromatic light in a wavelength lambda versus lambda plus d lambda. And these two different wavelengths will give you kind of two different response levels plus noise. Yeah. And then you say whether these response, response in the three-dimensional space, RGB, we usually call it SML. They're separate enough that you can say they're different, otherwise they're not different. And so you can say, what's the minimum d lambda threshold necessary for you to do this? And you can do exactly the same Bayesian decoding kind of stuff, and you find that the theory, model prediction, and the data match exactly, except again, you have to scale by a free-fitting parameter. Yeah, and so all of these have the good news repeat that human and animal decoding follows the same trend as predicted from optimal decision from the retina and V1 signals. And the bad news is by a big margin that we human, the whole animal is performing very, very poorly. Yeah, that's very strange. And so somehow there is a limitation. It's in the central brain and not in the retina. And is this related to attentional bottleneck? We can ask that question, yeah? And you can see, do humans follow priors? Yes, they do. We have all these kind of things. For instance, you can see that this is a kind of a bulging convex thing, and there's a concave thing here because you have a prior to think the light comes from the top. And of course, you can trump that prior by knowing the hand is always bulging, regardless of whether the light comes from top or bottom. Yeah, so you can another prior trump the other, the first prior. That's possible, and sometimes the prior can be so strong that you just can't help it. Yeah, and so you somehow always see the face is bulging up because the face should be going this way. And so all of this, and here is another situation that you can also follow the prior expectation for the likelihood. So for instance, if you look at this, you say, oh, is there a vertical bar in this gap or vertical bar in this gap? You will say, well, maybe here, but definitely not there. Is that right? Okay, let's see what's going on. If I occlude that area, I say, is there a vertical bar behind the occluder? You say, yeah, maybe most likely. Is there a vertical bar behind that occluder? You say, yeah, most likely, and the likelihood in these, you would think the same, yeah? However, if you take it away, somehow you think it's more likely here. What's going on? That means you have the same prior if you don't see the data. Once you see the data, somehow you think this is because the likelihood that the data is like this, given the context, is much higher here than that here, yeah? And so therefore this, are we seeing ghosts? Seeing is believing. In this case, believing is seeing. You believe something is there, you see it. Yeah, it's like seeing ghost in a dim room, but seeing ghost under bright sunlight, you don't see it. Ghosts like to come in a dim room. Yeah, so that's also kind of interesting. But anyway, do you do Bayesian decoding in the brain? As you know that a lot of these toy examples usually involve very simple decision making between two alternative choice of A versus B and all these kind of things, only one-dimensional value for S and so on. But if it's multi-dimensional, then you cannot do a probability distribution in a multi-dimensional space trying to do decoding. It's just exponentially combinatorial exploding, and it's difficult. And we can see that it is difficult here, right? If I don't give you the hint, you may not see the duck. Because what is it? You're not giving me just choosing between A and B, you're choosing between how many possibilities. I have no idea, yeah? And that will be really, really difficult unless I give you a hint. And so therefore, if you give you a hint, you say, oh, what is this hint coming from? Is this hint what the higher brain received from the initial feed-forward processing of visual inputs? Yeah, is it possible? So now let's go to the interesting bit. Is it really the case, possibly, that the feed-forward giving you a hint? And of course, we use a lot of feed-forward neural networks in artificial and in natural brains. And this is our natural brain. A lot of these links, you see, I do not put any arrows for indicating direction because most of these connections, or many of these connections, are actually reciprocal. So there's lots of feedbacks in the brain. Yeah, so retinal to LGN is either have a direction there. This is actually feed-forward, but LGN to V1 is reciprocal, and V1, V2 is reciprocal, and V1, V4 is reciprocal, and so on. Yeah, there's all reciprocal. So here are the latencies. If a visual input onset is time 0, 40 milliseconds later, V1 start to respond. 70 milliseconds later, V4 responds. 100 milliseconds later, IT respond. And by 125 milliseconds, this is work by Hong et al. In 2005. You can look at 300 IT neurons, and then you can use these 300-dimensional vector of responses to a linear classifier to classify into 8 different categories of visual objects quite well. And so that's not too bad. Yeah. However, if you make some classification image really difficult, and these difficulties are such that even CNN networks find it difficult, okay? And these ones you find that, well, if you just wait 125 milliseconds, it doesn't do very well either. You have to wait a bit longer, yeah? You have to wait till 150 milliseconds, which is only 25 milliseconds long, but longer, but nevertheless, now you can discriminate these, classify these objects better than just purely feed-forward at 125. So from 125 to 150, some recurrence processing is going on, yeah? And so therefore, this is one indication. This is not only seen in monkey, but also in seeing human patients who are in need of brain surgery. You can actually observe them a little bit, yeah? And so longer time involve can enable a bit recurrent iterations, yeah. But the question is how, yeah. Of course, the R vector, the response 300-dimensional R vector at 125 is different from 150. How did it happen? That's the critical thing. You know, once you give you the R, you can decode. That's kind of a little bit, you know, how does the brain do that? Okay, and so here's the, now we have already think that V1 start our initial eye movement. So therefore, if the eye movement guidance is already happening in V1, if you want to not waste your time, you better start selection right there. And so that's a motivation, so selection starts at V1. So here are the evidence showing this V1, but anyway, then what should decoder do in light of it? So this is the first kind of a question we could ask, or can say, what could it be? First of all, traditionally, I don't know. We still don't know. So this is the first attempt. So we have a hypothesis saying now you should distinguish between central or peripheral, okay? So the whole idea is the V1 make you move your eye. Imagine you're looking at this image and suddenly say, oh, well, this location, I move my eye to it. Now that location is not in your central visual field. Once you move your eye to it, it's in your central visual field. Then you feed forward, and that should be where your attention is. You should process a bit more than whatever you did not move your eye to it. So there must be a difference between central and peripheral. Well, if the bottleneck already started here, so all little information going forward, well, what if you still can't see what this is? Is it a flower or a red apple? Then you say, it could be either be flower or red apple. It's no longer like the duck. I have no idea whether it's duck or it's a tree or a house or whatever. But here it's just two choice, flower or red apple. You already narrow it down. Then you can say, well, I know the red apple should look like this, flower should look like that, and then go back and fetch more information from V1. Because now you have a specific information to ask between two categories. Does that make sense? Okay, so therefore you need to go back in your attentional bottleneck. It's only just two pieces of, between two categories, you can actually squeeze through this bottleneck and still go ask the information. However, peripheral is not where you pay much of a resource, attentional resource. So maybe they only have feedforward. So that's the first dichotomy hypothesized to happen. So let's see more detail. Retina comes to the, imagine you already move your eye and put this thing, you haven't recognized this thing, into the center of the visual field. Okay, you already gaze shift, look at that. And now, information bottleneck starts. Some information get deleted. I just do a cheap metaphor of deleting some pixels just to show that some information is gone. Okay, is there really information gone? Yes, we have evidence. Eye of origin information is lost. Remember, by V2, you don't know whether it's left eye sees something or right eye sees something. So at least some information is gone. Yeah. Secondly, the V2 received fields are actually bigger, by twice as big. So some spatial detail is lost. But anyway, we don't know whether it's 50% lost, 100%, 99% lost, but it's quite a loss. But let's say it's lost a little bit at least. Even in central visual field is lost such that you cannot tell what is this? Is it a leopard? Or is it a flower, a red, yellow flower? You don't know, okay? And so you go back and say, tell me a bit more, is it a leopard or flower? So you query for more information in central vision. And you don't query as much there. So what will be the consequence? The first consequence is peripheral vision are more easily fooled. Well, if you can't query, you say, what is this? This looks like a stick figure. Maybe this is an elephant, yeah? So you might see an elephant. So therefore, peripheral vision are more easily fooled and you must have illusions, yeah? And central vision were less easily fooled, no? Okay? And central vision more likely to be biased by feedback process of prior belief because you believe a leopard should look like certain ways. So you can imagine central vision should have these kind of symptoms. Do we see it? Let's see, okay? That's one way to falsify and test this hypothesis between central peripheral dichotomy. And central vision should also have a strong effect due to backward masking. Imagine you have an input A immediately followed by input B. By the time you say, oh, what is this input A? Is it a leopard or flower? Then you go back and query for more information. By the time you go back and query for more information, input A disappeared, input B is there. What would you do? You're going to get confused, right? And so central vision is going to suffer for these things. It's called backward masking. This is the psychological study of feedback. And you can say central vision should suffer from that more than peripheral vision because peripheral vision does not go back. And just whatever you tell me, it's a stick figure, I believe it. Yeah. So let's see. We can study this to test our central peripheral dichotomy and to probe feedforward and feedback process in the brain. So do you see? Peripheral illusions, seeing flashes only in the peripheral vision. Remember, our central vision is only about 1 degree wide. It's really is a tunnel vision, okay? So anything a little bit further away, so imagine if you're fixated here, this is already peripheral, okay? And that's it, all these flashing things. Do you see rotating snakes? But wherever you stare at, it's not rotating, isn't it? Yeah? And so here's another example, yeah? So now, if we understand V1, remember V1 is kind of our treasure chest of lots of knowledge about physiology, yeah? Then in this framework, can we predict illusions? Unlike traditional psychology vision, you just accidentally discover illusions by chance. Now can we predict? So let's try to predict. I'm going to predict something to you. Here you see lots of vertical pairs of dots. This is not illusion, okay? These are called homo pairs because a pair of dots, they have the same color, either both white or both black. And here is another picture of lots of vertical pairs, but we call it hetero pairs because one black, one white each, and they all look vertical. And I'm going to tell you that if you direct your gaze here and see this in your peripheral vision from the corner of your eyes, you should see them all horizontal. You can tell me, gee, I'm not convinced. I say it's illusion, but you're not convinced. So let me show you another demonstration of this illusion, okay? So here is a demonstration. If you fixate your cross, fixate on your gaze on a cross, do you see a ring? Yes? No? Yeah, okay. It's not an illusion. This is a baseline, okay? This is because along the tangent of the ring, lots of these homopairs align with it, okay? It's not an illusion. Now I give you B. You fixate here, now do you see a ring? Yes, no? Yes, okay, you can see yes. Okay, but you no cheating, okay? Fixate here, no cheating. You see it? Difficult, yeah? Well, the only difference is that every second pair, it becomes a hetero pair. Remember, I said hetero pair, you should see illusion of being orthogonal to itself, yeah? So if you fixate here, this is your peripheral vision. So even though it's tangential, you see it's perpendicular. That's why, so originally everything is tangential along the ring. If it becomes perpendicular in peripheral, you just break the ring. That's why you don't see it, yeah? Okay, you see, I'm not convinced. You said this is the thing. So what if I make it perpendicular? Then I should see it parallel. Then I should see the ring again, yeah? Shall we try it? Let's try it. So now let's have a third case where everything is the same, except now it's perpendicular. But if you fixate here, it's in peripheral vision. I told you that reality is you see it's parallel to it. Okay, so the only difference is this is parallel, this is perpendicular, but if you fixate here, and then in both you fixate, in B and C, which one is more easy to see the ring? B, yeah? So here's demonstration. Indeed, this is an illusion. It's in your peripheral visual field. They say, how did you predict it? Oh, it's very simple. Because in V1, we have these Gabor filters. Imagine here's a one particular Gabor filter. It's for horizontal orientation. Here's the off subfield, here's the on subfield of Gabor filter. And you put a black dot in there, white dot in there. It's a vertical pair, but activate this horizontal cell. Does that make sense? Yeah? Okay. But this horizontal cell can also be activated by a horizontal pair of homodots or even Gabor filter. Yeah? So this horizontal cell can be activated by this, and many other possibilities. But if you put this vertical pair in a vertical tuned cell, it will not be activated. Yeah, okay, no problem. Okay, now imagine your retina has this vertical pair and it goes to V1 and activate this V1 cell, happen to be that cell, and this V1 cell, let's call that cell Mary, okay? Mary, out of 100 million cells, Mary is activated by this input. And let's imagine the bottleneck starts in V1 such that this is the only cell from V1 sending information to V2 and all other cells are not sending any information. Is it okay? So therefore you have to do decoding from this cell alone, not a population decoding. Because that's an extreme case of bottleneck. Only this cell sending information forward, this cell sending information forward, and higher visual area say, oh, cell number 8 firing a lot. This cell number 8 is tuned to horizontal. If it fires, it could be this input, that input, this input, this input. I don't know which one, or could majority vote horizontal. Does that make sense? So if it has to rely on only one cell because of information bottleneck, no other cell sending information, it will be stuck with this thing. It cannot, that will be the illusion. However, you say, wait a minute, can I go back and, just to check in case it's that maybe, so you go back and check. Now, by the time you go back to check, you already know this is cell number 8, and cell number 8 is Mary, tuned to horizontal, it should be this way. Therefore, you can go, wow, actually it's that. Then if you go back to check, you will not have this illusion. Does that make sense? And so this is called, I call it feedforward, feedback, verify, and we will wait. So the idea is you weight these different hypotheses. This hypothesis is 1/4, this is 1/4, 1/4, 1/4, and you say, okay, these are all horizontal. But once you verify you weight this hypothesis higher. Does that make sense? So it's feed forward, feedback, verify, and reweight. This is FFVW. And central vision enable you to feedback. Therefore, central vision doesn't get fooled. It's the peripheral vision that gets fooled. Does that make sense? That's how it works. And you can even do the tilted resistive field in space-time, not just space-space. And therefore, space-time tilt is motion. Does that make sense? So you can have y dot x1, t1, and y dot x2 and t2. That's a particular motion. However, if move from the x1 to x2, no, actually move the other way around, then this cell will not be activated, right? So this cell is selected for one particular direction of motion. However, if you make it black, suddenly the cell will be activated. Does that make sense? So therefore, if you not only move in space, but also change from white to black, you can fool this V1 neuron to thinking something else. And that's exactly what happened. Here, do you see it's white and black flashing? That's how you see that this is keep on moving forward. Turns out it's black, black, white, white, black, black, white, white. It's just switching. Okay. So when it's moving forward, it's a real motion. When it's moving backward, it changes polarity from white to black or white. And so every time the neuron thinks it's moving forward, that's why I think it's moving that way. Okay. So now we understand, well, this is why this illusion is so strong. Yeah. And you can do it in analogy into stereo vision. Here you have two eyes rather than two time slices. And here you can have a pair of black dots. This is equivalent to that. Black dot, a pair of white dot, and is equivalent to that. And you know, this central disk is, if you have a particular binocular disparity, I just moved, yeah? Particular binocular, it will make you see this disk is in front of a ring, okay? That's the binocular disparity. Now let's do an analogy where a white dot in one eye corresponds to a black dot in the other eye. It will correspond to these heteropairs. And remember, heteropair always see the opposite. You know, orientation opposite is orthogonal. Depth opposite is whatever in front, not it says behind. Okay, so the V1 neuron will respond as if this depth, this disk, even though the binocular disparity says it's in front, none of the V1 neuron activated are neurons who prefer back. Okay, and then what do you see in your central vision? You don't see it's in back. What's going on? Central vision does not get fooled. Yeah, remember, central vision can go feedback. So what happens is this V1 neuron says in the back, not in the front. Okay, feed forward this reverse depth to higher brain areas. Top down higher brain area says, well, it looks a bit noisy, let me check. Okay, when I come back and check and say, gee, it looks like the disparity is not what I expect, it should be back. And worse yet, a black dot become a white dot in the other eye, that you're telling me fake news. And so therefore veto the fake news, therefore you never see the fake news. Well, without fake news, there's no real news, so therefore you see nothing, neither front nor behind. Now, if that means the top-down feedback in central vision enables the vision not to be fooled. So enable the vision not to be adversarially attacked. Yeah, that's what it means. Okay, and so now you say, well, sometimes you don't have feedback. Then you will just believe whatever fake news tells you. That's why in peripheral vision, you should be able to see that this disk is now in the back. And that's a prediction. And that prediction is then indeed confirmed. And therefore, you only see this illusion in the periphery. And that's confirmed. You do see in the central visual field. Okay, then you say, but didn't you tell me you're going to do some top-down feedback? You just tell me central vision not getting fooled, but let's see some central vision do better than not getting fooled. So to study feed-forward and feedback processes more than just not getting fooled, shall we do something intelligent? Yeah, well, not getting fooled is being intelligent, something else intelligent. So imagine now you're going to have a hybrid random dot diagram such that you have not only same color, you know, matched color in between two eyes, and you also have the non-matched color. Okay, you just mix these two. Some are fake news, some are not fake news. So you mix it together. Okay, and turns out that you will have these kind of phenomena to happen. That means if the fake news and real news tell you the same thing, you see better. Okay, so this is in the case like a fake, you know, you see the partial signals of the triangle, but you see the whole triangle. You can somehow, you know, use like a fragment of information, you combine them together, even though they're not perfect. You take advantage of it with your top-down knowledge, and you see better when this, let's say this is telling you behind, this is also telling you behind. You can combine these together, you see behind even stronger. Okay, so that is really useful. So same thing here, you say, well, I'm not seeing what, but once I tell you it's dark, then suddenly you see the dark very vividly. So this is the top-down imagination that make you not only not getting fooled, you have that, you can say in machine vision, maybe you call it generative models, yeah? You know, this is Helmholtz machine, top-down feedback, general model, yeah? And these kind of things, you can do that. And here is you show you that your top-down bias, because you already think that the flower should look like that and leopard look like, it will give you a bias. Let me show you an example. Imagine you show this to the left eye, this eye to your right eye. They are specially designed such that if you add them together, you will see a stripe tilted clockwise from horizontal, okay? And if you difference to each other, you see a stripe tilted anti-clockwise, for example, from horizontal. Now, if you come to my the second lecture in the morning, I have already explained to you that in V1, in fact, the two eyes are combined into these two new channels, which is the PC and component channel, yeah? Some of you are here, yeah? You remember that? Okay, very good. So this is the PCA component in V1. So in V1, you see some tilt this way, some tilt that way. So if you show this, let the people wear stereo goggle and let them see this. This is in left eye, this is right eye. You ask them, is it tilted this way or that way? People tell you, gee, I'm not sure. Then you say, well, you just have to give me a false choice answer, this way or that way. And turns out that they will most likely, you know, 2/3 of time tell you tilted that way. But you have designed it such that they have the same contrast input strength. How come they're biased to see that? Okay, now let me explain to you. So the idea is, imagine V1, some of the neurons says tilted this way, some of the neurons say tilted that way. Remember, by the time after V1, it no longer tell you whether it's from the left eye or right eye. Remember? That also means after V1, it doesn't tell you whether it's coming from the two eye add together or two eye difference. It deleted that information from V2. So it only sent that tilted one way here, tilted one. So let's imagine this is telling high visual area, oh, it's tilted clockwise from horizontal. And the higher visual area says, if I perceive it tilted this way from horizontal, it's likely that both eyes should have it in my left eye and right eye. Does that make sense? Because that's what I expect the world should be, yeah? And therefore, so it should resemble the input in the sum channel. It should resemble this input. So therefore, it goes back and verify and say, oh, looks like it's correct. So tick, correct, yeah? Okay, now the other channel says tilt the other way. Well, it will do exactly the same thing with its own imagination. What should be like, it will go back and check with that channel. Does that make sense? And when they check that channel, say, no, this channel doesn't say it's tilted this way. So therefore, veto, yeah? So therefore, this is confirmed, this is vetoed. So therefore, this is of course called analysis by synthesis. Again, this generative model, you analyze what the input should be by synthesize what it should be and compare with the actual input and see whether they make sense. Does that make sense? So you can say this is a form of visual understanding. And this understanding comes at a cost because you're putting whatever your bias on what input should be, yeah? And this is indeed the case in human behavior. And again, this is feed-forward, feedback, verify, and reweight. Originally, these two feed-forward weights are equal, 50-50. After you verify, this maybe become 90%, or in this case, it's 2/3, and this is 1/3. You start reweighting. Yes, please. A bit louder, please, so everybody can hear you. Yeah. Yes, this is actually done. Very good. You are thinking quickly. And this was actually done in a separate experiment. Indeed, by manipulating correlation, you actually can also change the bias. Yeah, and that's of course it's in the encoding stage. This is top-down bias even without manipulation. You're right. Very interesting. Yeah, and this was actually worked down mainly by my postdoc, who's now working in London. Yeah, and he's now a faculty member in London, and his name is Keith May. And turns out that if you do this in peripheral vision, you don't have this bias. It's 50-50. Yeah, and so this gives the hint that this bias is in central vision stronger than in peripheral vision. In this case, peripheral vision actually has no bias. But you say, wait a minute, shall we do something else? It's not tilt perception. How about color perception? How about motion perception? Turns out that depending on what perception, what visual feature you're trying to do this decoding on, you find this this bias in peripheral vision, sometimes it's not 50-50, sometimes higher, but it's always lower than central vision. Central vision always has stronger bias. So therefore, you can feedback in peripheral is there maybe different, it's just weaker than central vision, depending on which channel it is, yeah? And yeah, that's what happens. And so anyway, I just put it together. You have all these illusions, which you can see them as adversarial attack to our visual system, and the machines get these adversarial attack. We humans also get it, but we humans have central vision, which do not get so easily attacked. And you may say this is that we humans have understanding. This understanding is in central vision through top-down feedback, through internal generative model of what the visual world should be, analysis by synthesis. And you may say the current machines may only imitate the human peripheral vision, yeah? And so therefore our human central vision can make us do these kind of intelligent behavior, which is beyond surviving the adversarial attack, yeah? And with this, I'm a little bit, yeah, so therefore we're able to make this fresh progress by reframing what vision is. Basically, it needs to acknowledge there's a selection right starting in V1, and with that, the decoding need to be understood in a different framework, in a different algorithm, and maybe that will have fresh progress, yeah? And yeah, that's what I'm going to do. And the next lecture, I'd like to have more exchange with you, because we were going to dive deeper into the difference between between the machine and human vision, digging deeper into some of the questions we don't even know the answer, but hopefully they are provocative, that to make us think, you know, because after all, we need to be kind of feel defeated by some kind of wonder, but there is an existence proof in nature that this wonder exists, yeah? And I'd like to also, you know, invite you to join us, so therefore the human natural vision and artificial vision can work together, you know, because maybe we can borrow a different approach to combine to some solutions together, yeah? Okay, see you, yeah.